Okay, welcome back, everybody. For the very last session of the workshop, it's very sad, actually. I'm very sad. So the next speaker is Svoboda, sorry, who is going to speak about AGN spectral state and their radiomorphology. And I see that Cagliari is starting to share the screen, but we don't see the presentation yet. Guess I have a problem now.
Is about the spectral states in active galactic nuclei, so the supermassive black holes, and mainly with the focus on how potentially the radiomorphology can be related to accretion state or to accretion state evolution. And this work was done in collaboration. And mainly, I would like to mention the young postdoctoral researchers in Prague doing the most of the results that I will be presenting in the radio. And this is Emily Morejvek and Abhijit Borkar. So our aim is to understand the link between the supermassive black holes in AGN and X-ray binaries, and mainly whether the accretion and ejection phenomena are to somewhat degree similar, and with the focus whether the large jets that we observe in AGN, in some AGN, the radio loud AGN, not in all of them, might be also related to spectral state similarly, like for X-ray binaries, when the jet is present in the hard state, but not in the soft state. So just briefly about the spectral states in X-ray binaries, I think it was introduced in several talks already during this workshop. So just emphasize that in the soft state, the spectrum is dominated by the thermal disk emission. And in the hard state, there is very strong hard X-ray emitting corona and much weaker of the emission from the accretion disk, the thermal emission. And the most interesting are the evolutions between the different spectral states in X-ray binaries, and notably the presence of the jet, that this is always present in the hard state. Then during the transition between the hard to soft, there is ejection of relativistic plasma blobs in the jet direction, and then the jet is quenched in the soft state. And we would be mainly interested in AGN, whether also the jet is related to the accretion processes. So if the analogical state to soft state in AGN do have jet or not, and the hard states having producing the jets. And so for AGN, of course, the time scale and also the size scale is very different from X-ray binaries. So it is almost impossible to study individual sources, how they evolve, but instead it is possible to study a very large samples of AGN because we have a lot of sources. And even more than for X-ray binaries, for AGN is needed the multi-wavelength approach. And this is mainly because the disk around the supermassive black hole is much colder than in X-ray binaries. And so the thermal spectrum of the disk peaks in the ultraviolet domain. So when we want to compare spectral hardness for AGN, we cannot use just the X-rays, but we have to compare what is the flux in UV and what is the flux in X-rays. And a lot of previous work was done on this unification between these supermassive and stellar mass black holes. So I list here the references that we are building on in further analysis. So now I will go straight to the results that we obtain by analyzing the simultaneous UV and X-ray observation with XMM Newton. We had about 1,500 sources, and we built the hardness luminosity diagram. And the color in this diagram shows the radio loudness. The darker the radio louder sources are with respect to the X-ray and UV luminosity. Also, the side histograms show that the radio loudness is increasing towards the upper right part of the corner. So this is consistent with the previous results also obtained by Elmar Kerding before. And what we can see is that the radio loud sources are concentrated in the hard part of the diagram, and at the high luminosity, when we go to the left, to the soft, much less radio loud sources are present there. They are clearly dominated by the radio quiet sources. Here, these green crosses and cyan triangles. At low luminosity, it's a bit different than what we are used to for X-ray binaries. And I think that the main reason is the contamination of the host galaxy. to the X-ray and UV luminosities, because in AGN we are not looking at the isolated systems at all, but we are looking through the galaxy. And at some low luminosity, which is like 10 to 44, the host galaxy can dominate in the fluxes. And it is not trivial to decompose the host galaxy from the AGN flux for the large sample. And so what I plotted here is the AGN as well as the non-active galaxies, which are the blue crosses. And you can see that the distribution of non-active galaxies is really like going to the softer part. This is natural because the host galaxy is mainly dominated by the UV emission of the stars. So this is making the sources softer. So if we don't have a perfect tool to decompose the host galaxy from AGN, we have to live with the fact that the quiescence is not here to the bottom, but slightly to the left. Or slightly, it can be very, very going to the left. And so now I would like to focus on the new results that we obtained when we compare the position of the sources with different radiomorphology. So this most standard radiomorphology for AGN is the Fanarov-Riley classification that distinguishes two classes. The FR1 sources are sources with compact jet. Most of the radio emission is coming from the central part of the jet. And oppositely, for the FR2 sources, then much brighter is the radio emission from the edges of the radio lobes. So these FR2 sources corresponds to sources with more extended jets, with the radio lobes, with the indications of the powerful jets and before. Of course, this is not related only to the power of the jet, but it is a strong function also of the environment around the AGN itself. So it might be that FR1 sources can be really strong jets, but the environment is very dense, and so the jet cannot propagate, and vice versa for FR2 sources. And nevertheless, we looked at this position of the sources in the hardness luminosity diagram, and what we see is that the red sources correspond to FR1 classification, and the blue corresponds to FR2. And there is the separation between these two classes. And this is what we would expect from the analogy of X-ray binary, so that the more evolved jets coming later. You can see in the plot also the black contour line, which corresponds to the parent XMM mutant sample. So there are not many radio loud sources, as you can see, because the majority of sources are radio-quiet quasars. You can see also the dashed line, which is the Swift bus sample that we added to our original XMM mutant sample. And all the contours represent smoothed contours where within them 68% of sources are present. So then we looked also for sources for which we have measurements of mass. We look at the Eddington ratio instead of the luminosity. Eddington ratio is better proxy of the accretion processes because the AGN span a wide range of masses. Of course, the disadvantage is that we are then having less sources because not for all AGNs and distant quasars the measurements of mass are available. But as you can see on these two plots and compare them, qualitatively we are getting the similar results between the hardness luminosity and hardness Eddington ratio diagram. And then we looked at the excitation index, because this is also indicating what is the power of the accretion and radiation in the sources. Higher excitations means that there are more excited lines present in the optical spectrum, and low excitation means that probably the accretion is not radiatively efficient, and so that the stronger ionized or excited lines are not produced. However, here we see also the separation in similar way like FR1 and FR2. It's not maybe that clear like for the previous case. But then the last plot I would like to show is that when we combine both classification, and this is shown in this plot. So the red sources now are the FR1s, low excitation radio galaxies. Violet are FR2, low excitation radio galaxies, and the blue are the FR2 high excitation radio galaxies. So this should be those sources that have much more radiation coming from the accretion processes. And in the hardness luminosity diagram, they are, I would say, more clearly separated, and also there is a less mixture than when looking only for the FR class and excitation index. So this is the main result I would like to show you today, and this will be in more details discussed in a paper that is just before submission by Emily Moravec. And so my conclusions are that we studied the AGN with radiomorphology, and we compared their position in this hardness intensity diagram in analogical spectral state diagram for X-ray binaries, and that we see that these two classes are separated in what we would expect from the first approximation from X-ray binaries. So that's very interesting, because this might indicate that the AGN radioactivity and morphology might be indeed related to the spectral states and to the spectral states evolution, similarly to X-ray binaries. But of course, much more detailed work will have to be done to address this point in more detail. So thanks for your attention, and I will be happy for your question.
Thank you. Do we have questions? I don't see any. Yeah, Rob?
Yeah, thank you. Very, very interesting work. So Fernandez Ontiveros and Munoz Talias recently also published work looking at comparing X-ray binary states and AGN from the aspect of mid-infrared nebula lines. And they also came up with some specific conclusions on how particular X-ray binary states compared to particular classes of AGN, for example, Seyfert-2s. Have you had a look at that? And do you know if their results are similar in agreement with your own?
Mm-hmm. Thank you very much, and thank you very much for also your point, because I would like to mention also this analysis in mid-infrared, because for example, in our case, when we are looking directly for UV and X-ray, so like studying the accretion directly, we are suffering for especially low luminosity sources for this host galaxy contamination. And I think that in this mid-infrared method, maybe this problem is not that serious. And so then the combining and comparing directly the sources, if we have the overlap between our samples, would be really great also to address this in more details. Otherwise, yes, for like the general conclusions, I think that we are in good agreement. And yeah, that's really interesting also, these different approaches to reach the same goal and understanding of this AGN and X-ray binary unification.
Do we have a question in the room?
Yeah.
I would like to ask about luminous blazars. My impression, maybe I'm wrong, was that many of them are soft. They are in soft state. They have accretion disks without much accretion X-ray emission, and still they have very powerful jets. But I guess they were not included in this in your classification, right?
Yeah, exactly. We removed the blazars because of the strong beaming effect, which would affect the results. But yeah, that's really interesting.
But what are they? Yeah,
yeah, exactly. So also I did not mention also changing log AGNs that are like challenging this unification scenario if they are related to spectral state transition, and also that if you look at our results, you clearly see that there is a trend of separation that works on like on average on a statistical large sample, but there are many sources that are just not following exactly what we would imagine, like for X-ray binary analogy. So that's really interesting.
There is another question in the room, but
there was Greg first on the Zoom.
So have you looked at the Eddington rates of your sample? Because in particular, one of the things I'm concerned about is that we often talk about microquasars when we're comparing things in the sort of hard state or at much higher Eddington ratios, which might be not the hard state, but something more akin to the steep parallel state where we have seen radio signals as well in X-ray binaries.
Mm-hmm. Okay, the connection was not great, but I understood the question is about the Eddington ratio. So if you can show the presentation, I had at one slide the comparison between the hardness luminosity and hardness Eddington ratio diagram. I fully agree that the Eddington ratio is much better proxy, and also that for some sources that are just luminous quasars, but with a very large mass, it might be that they also go to different position in the diagram. So I can show you here in this, when we looked at the FR classification, the position of sources with different FR classification. So in the upper plot, you see the hardness luminosity, and in the bottom, you see exactly the same hardness Eddington ratio. Because the number of sources is significantly reduced when we need to have the mass. We would really like to have mass for more objects and work only in the Eddington ratio. But from these plots, you can see that like some points are moving up and down, but it's not changing the qualitative results.
Okay, maybe a last question in the room there.
Hi, thanks for the talk. I was wondering if you could try to include the FR0 radio galaxies in the sample, or if they're too contaminated by the host galaxy to do this.
Yeah, thanks for the question. Yeah, well, I don't have prepared these slides on this, but we also look at different classification, like also FR0s and the compact sources. It's getting a bit more complicated in the hardness luminosity diagram, but the plot will be at the paper that is in preparation.
Okay, thanks.
Thank you.
Thank you. So let's thank the speaker again.